Okay, so in this section of the lecture notes, we're going to start talking about things flying around in outer space. Satellites orbiting the Earth, planets orbiting the Sun, rocket ships launching out into the cosmos. So in the last homework set, actually, we saw that satellites flying around the Earth can be thought of as undergoing almost uniformly circular motion. And by the end of this section, we'll understand where that almost is coming from. Where the force of gravity is the thing supplying the centripetal force needed to keep changing the direction of the satellite so that, it's traveling around the Earth. Okay. So remember, if you have uniform circular motion for uniform circular motion, if what you want is to travel around in this circle, at any moment in time, say instantaneously, you have some velocity, right? And if there was no centripetal force, then the satellite, or whatever is undergoing this uniform circular motion, would just continue flying off in whatever direction it's pointing at instantaneously, right? That's how inertia works. So if this is the velocity, we know that there has to be some force pointing towards the center of the circle, some centripetal force. And for planets and orbiting objects, that force is supplied by gravity. And so it's the attractive force of gravity that's keeping a satellite, for instance, flying around the Earth. And basically what's happening when a satellite is orbiting the Earth is that the satellite is constantly free-falling, okay? But it's moving so fast that as it falls towards the Earth is, the Earth is roughly a sphere, it has curvature. The Earth kind of falls away from the satellite as the satellite falls towards it. So let's think about what this might mean a little bit. If you're standing on the ground, you're standing on the ground and you're winding up and you're, gonna launch this tomato or whatever. If you throw this with if you throw it with some initial velocity that's pointing horizontally to the right, what's going to happen? It's going to take some trajectory. Its rightward velocity, as long as we neglect air resistance, is going to stay constant throughout the entire trajectory, but gravity is going to act on it, and so it's going to fall towards the ground as it travels to the right? And so gravity acts, and the tomato hits the ground. You throw it a little bit faster, and it still covers the same vertical distance in the same amount of time, but because it's traveling faster, it's able to get farther before it hits the ground, right? So the faster you throw it, the farther it gets, even though it takes the same amount of time to cover this vertical distance, okay? Well, what would happen if we were able to throw this tomato not just really hard, but unbelievably hard, and get it up to enormous initial velocities? This was a thought experiment that was done by Newton. It's traditionally called Newton's cannonball. So here, I've drawn the Earth. It's an extremely good drawing of the Earth, I have to say. And what we imagine is that there's some, not to scale cannon sitting over here, and it's going to fire a cannonball, right? And, if it fires it, like a normal cannon, on this scale of the drawing, the cannonball would just barely move anywhere relative to the curvature of the Earth. But if it was fired fast enough, it would start falling, but the curvature of the Earth is falling away from the cannonball. The ground, because of the curvature, is falling away. And so as you fire faster and faster, this cannonball is able to make it farther and farther before it hits the ground, right? Until eventually, at some speed, actually, it's able to execute uniform circular motion, where the rate at which the ground is falling away from the cannonball kind of coincides with how much vertical or horizontal distance the cannonball is covering, right? So at a sufficient speed, actually the cannonball makes it all the way around. Now, if it goes even faster, you start to get non-circular motion, and we'll understand that a little bit more by the end of chapter 5. This is meant to be an ellipse. I'm actually so bad at drawing that I might as well just drag in. This is Newton's original illustration, published posthumously, but this is from like the 1720s or something. And so you can see what I've very terribly attempted to draw up above, as my computer seems to have crashed. Great. I don't know why I can't. There we go. Okay. So, you've got a cannon sitting on the Earth at kind of fast but reasonable cannon speeds. The cannonball travels a little bit. The faster you give it some initial velocity, the farther and farther it makes it around the world before it hits the ground, until eventually the cannonball is traveling so fast that it is in constant free fall, but never makes it to the ground because the ground is curving away from it. and it's this circular orbit. And then if you fire it even faster, it will approach one of these other types of trajectories, which are not circles, but actually ellipses. And we'll see what that's like in a little bit. Okay. So if we neglect things like air resistance, or the possibility that this cannonball is going to crash into a tree or a mountain or something before it starts orbiting, once we set up this flight, the cannonball will keep circling the Earth forever, right? It's just got some velocity, some instantaneous velocity, maybe over here, and it's pointing in this direction. It's constantly feeling a force, the force due to gravity, and that's pulling it towards the center of the Earth along any of these trajectories, any point on this trajectory. But it travels so fast that the ground falls away at just the right rate for it to kind of make it all the way around the world. Okay. So this thought experiment is actually basically how we should be thinking about orbiting celestial objects. So the particular path that an object takes, if it is free-falling around some celestial object, like a planet or a star or whatever, these paths are called orbits. That's what the word orbit means, orbits. And the time to complete one full trip around an orbit, that's called the orbital period, is the orbital period. Okay. And the orbital period of an object ultimately depends on how far that object is from whatever it's orbiting around. And to see why that's the case, let's think a little bit more about the force of gravity. So the orbital period depends on how far the orbiting object and the celestial body are. Okay, let's see why by thinking about the force of gravity. You see, the ultimate reason why this is going to be true is because gravity is the thing supplying the centripetal force, and the strength of gravity depends on how far apart two objects are. Let's see what that's like in a little bit more detail. Near the surface of the Earth, so near Earth's surface, we've said things like the acceleration due to gravity is like 9.8 meters per second squared. Right? And in some of the homework problems and in some of the previous lecture notes, we've kind of said, oh, well, if you're in different locations on the Earth, this number is a little bit different. If you're near the equator, it's a little bit less than if you're at the poles, things like this. So, this idea that the force due to gravity is basically m times g if you're near the surface of the Earth, this is just an approximation. It's typically a pretty good approximation, and good enough for a lot of the things we want to understand, but it's an approximation nonetheless. One of the things that Newton discovered was the so-called universal law of gravitation. Universal law of gravitation. And what he actually said was not just, the force that the Earth exerts on an object near the surface is given by the mass of that object times some constant. What he actually said was that the force due to gravity between any two objects, right? Whether that's the Earth and the sun, or the apple and the Earth, or two pieces of fruit in a basket, or me and this laptop screen, doesn't matter. The force between any two objects has the following magnitude. The magnitude of that force is given by some constant called g, multiplied by the masses of each of the two objects that we're thinking about, divided by the square of the distance between them. Okay. So if I have object 1 with mass 1 and object 2 with mass 2, and those two things are the distance r apart, the magnitude of the force due to gravity is given by g times m1 times m2 divided by r squared. Okay. And the direction is an attractive force from one object to another. So the force due to gravity, so we'll just call this attractive. So the force due to gravity acting on object 1 points towards object 2. The force acting on object 2 points towards object 1, right? So if I want to know what is the force due to gravity between these two pens, I guess I should try to hold them both in one hand so that I can actually point. The force on this black pen due to this silver pen points from the black pen to the silver pen. It points this way. And the force on the silver pen due to the black pen, due to gravity, points, that way. Great. Okay. Okay, I'm putting a big box around this because this was and is quite important. You know, the idea that the forces supporting celestial objects are the same things as the force support, acting to make an apple fall down on our head if we're sitting under a tree, that is not a kind of trivial or obvious observation. And even though this basic idea is taught in schools all the time now, it really took an intellectual leap to try to say the same thing, supporting the stars in the sky and the motion of planets is the same as the kind of feeling of gravity that we experience all the time in our daily lives. Right? So just to kind of complete our understanding, why does this approximation kind of square with this actual universal law of gravitation? Well, first let me tell you, this constant g, this is a fundamental constant of nature. Like, as far as we can tell, this is just the way the universe works, that there is a absolute constant sitting out here. And when we try to measure what this constant is, it turns out to be something like 6.672 times 10 to the minus 11, and it has units of newtons times meters squared divided by kilograms squared. And you can kind of figure out the units by saying dimensional analysis, right? We know what the dimensions of a force are. We know the dimensions on the right-hand side are the dimensions of whatever g is times 2 powers of mass divided by 2 powers of length. So in order to get those units to agree, Newton meter squared per kilogram squared, that's what this g has to kind of carry around with it. Okay, so why do we just say like force is approximately equal to mg? Let's plug in some numbers, right? So if we say the force due to gravity, well, we've got this g, and so that's 6.672 times 10 to the minus 11 newtons meters squared per kilogram squared. We've got the mass of, say, the object near the surface of the Earth that we care about, so I'm just going to call that m1, and I'm going to pretend, or I'm going to say for this calculation, m2 is the mass of the Earth. You might wonder how much is the mass of the Earth. That's more or less 5.972 times 10 to the 24 kilograms. Okay? Divided by, well, near the surface of the Earth, the distance between the center of the Earth and whatever object we're trying to work out the force of gravity on, you're basically the radius of the Earth away from the center of the Earth. And the radius of the Earth is, it varies a little bit because Earth is not a perfect sphere, but it's kind of pretty close to 6,370 kilometers squared. Okay, and if you multiply those numbers together and keep track of all your units, what you end up with is the force of gravity due to the Earth acting on an object whose mass is m1 is m1 times 9.82 newtons per kilogram. Newtons per kilogram, also known as meters per second squared. Right? And so there you go. That's kind of how, our estimate for how gravity works near the surface of the Earth actually stems from this much more general universal law of gravitation. Now, why did I go through this in the context of talking about orbital periods depending on how far away two objects are? It's because, again, the force keeping, say, a satellite in orbit around the Earth is the force of gravity between the satellite and the Earth. The force keeping the Earth in orbit around the Sun is the force of gravity on the Sun acting on the Earth. Right? So for orbits, gravity. Ooh, it's a rough G, isn't it? Gravity supplies the needed centripetal force. Centripetal force for an object to turn, right? To turn in a circular orbit, or later we'll see an elliptical orbit, to turn and move in a circle. Okay, and we saw in the last chapter that if you have uniform circular motion, the centripetal force was directly related to both the square of the angular velocity and to the radius, right? So we said for uniform circular motion, we said that the acceleration needed to change the velocity vector so that instead of flying off, it turned in a circle. The acceleration, which is the same as the centripetal force divided by the mass of the object was equal to, say, the angular velocity squared times the radius. Okay, well, if the centripetal force is coming from gravity, right, so if centripetal force, we plug in this expression, right, F centripetal equals G times M1 M2 divided by R squared, you see that we can rearrange this equation. So let me actually first write that out. Taking this equation, that would go to G times M1 times M2 divided by R squared, and then divided by M1. And so we see that actually these masses cancel out. That's going to be equal to omega squared times R. Right? And so rearranging this a little bit, what we see is that omega squared, the angular velocity, how much of the circle does the orbiting object go through per unit time, is given by this universal constant, g, multiplied by whatever the mass of the Earth is. So if you like, 2 is the mass of the Earth in this example, for a satellite orbiting the Earth, divided by 3 powers of r. 3 powers of r. Okay, and so we see, for cases where the centripetal force is supplied by gravity, because gravity gets weaker the further away two objects are, the angular speed is inversely proportional to some power of how far away the orbiting object is. So intuitively, if you're just above the surface of the Earth, you need to launch something at incredibly fast speeds for the ground to fall away fast enough, in the time it takes the object just to fall a few inches, basically. On the other hand, if you're far above the Earth's surface, then you need to travel more slowly so that the rate at which it's falling towards the center of the Earth is balanced out by the curvature of the Earth, by the radius that you're orbiting around. Okay, so at some point, when you get to a certain, say, distance above the Earth's surface, you can find yourself in a geosynchronous orbit. So around 36,000 kilometers above the Earth's surface, that's kind of the distance at which the orbital period, the length of time it takes for a satellite to go all the way around the world, is about 24 hours. Okay, and for these geosynchronous orbits, that means that if you're standing on the ground, once every 24 hours, you'll see a satellite come back to exactly the same point in the sky. A special case of these geosynchronous orbits are if you have a geosynchronous orbit above the Earth's equator. So above the Earth's equator, this is just like a fun fact, if a satellite is traveling east, then the way that it's free-falling around the world exactly matches the rate at which the world is turning, right? And so to an observer on the ground, it will look like the satellite stays exactly above the same spot of the Earth all of the time. And so that's the mechanism by which you can have geosynchronous satellite orbits. You don't need to constantly exert forces to keep a satellite in the right spot. You just need to launch it into a trajectory that's at the right distance away from the Earth, above somewhere in the equator. Okay, that's just like a fun aside as we understand how things in the world work. But as I mentioned, if you actually look at the orbit of, for instance, Newton's cannonballs, if you have them launched fast enough, or if you look at the orbits of planets, not all orbits are these simple, uniform, circular motion kind of circles. So that's probably something you intuit from the fact, if you learned this in school, that the Earth and the Sun are not the same distance away from each other all year round, right? When it's, I think, winter in the northern hemisphere, the Sun and the Earth are actually closer to each other, and when it's summer in the northern hemisphere, the Sun and the Earth are a little bit closer, right? So orbits don't have to be circles. Orbits don't have to be circles. And it was a famous astronomer, Kepler, who, before Newton wrote down his laws of motion, Kepler worked off of data to try to formulate laws of planetary motion. So this section is going to be learning about Kepler's laws of planetary motion. As an aside, so Kepler took data from this Danish astronomer, Tycho Brahe, sometimes pronounced Brahe, depending on what language you're pronouncing it in. And Tycho was a Danish astronomer who had a very interesting life, let's say. When he was a student, he got into a sword fight, arguing with another student about who was better at math, and he lost most of his nose in that duel because he was better at math than he was at sword fighting, I guess. And one of the things that this person did was just take meticulous data over years and years of observations, staring through telescopes in the sky, plotting relative to the Earth, where was, Mars and Venus relative to the Earth, how did it seem the distance from the Earth to the Sun was changing, all these things. And so Tycho had these tables and tables and tables, books full of data that kind of described what motions through the sky were different celestial objects following. And Kepler looked at all of that data and formulated three laws of planetary motion. That described accurately all of the data that this other astronomer had been compiling over years and years. So let's learn what these three laws are. Kepler's first law says that planets move in elliptical orbits. Now, you might remember from geometry that an ellipse is not just any random oval. It's a particular generalization of what we mean by a circle. So an ellipse is a shape that looks like this. And the way you determine the shape of an ellipse is you say, I'm going to start with 2 points, and those are called the foci of the ellipse. So let's label these as foci. And the ellipse is defined by this set of points, this like black elliptical shape that I've drawn. And that shape is defined such that if you look at these two distances, so I have R1, say the distance from a point to this first focus, and R2, the distance from a point to the second focus. The ellipse is defined by, all points such that R1 squared plus R2 squared is equal to something, okay? This is like a generalization of a circle, right? A circle is defined by, if I say I have a center of a circle and I label the distance between a circle and any point R1, the circle is defined such that R1 squared is just equal to, whatever the radius of that circle is. So you can see that a circle being the set of all points a certain square distance away from its center is like a special case of an ellipse being the set of points whose sum of squared distances from its 2 foci are a certain number. Okay, so for a planet orbiting the sun, let's say here's Earth. One of the 2 foci is the sun, and the other focus is just some empty point floating in space that doesn't move. Okay, so the Earth takes an elliptical orbit around the sun, where the sun is one of the 2 foci of the orbit of the Earth. Okay, so this is like a little bit of a generalization to the way we've been thinking about, uniform circular motion. Real orbits don't have to be circular, okay? Kepler's second law says that they don't have to be uniform in speed either. Kepler's second law says that orbits don't have to be constant angular velocity. If the orbit is circular, that's fine, then they will be, but in general, they don't have to be. Actually, we recognize this if we think back to our conservation laws. This is actually a consequence of the conservation of angular momentum. The force of gravity from, say, the force on the Earth due to the sun points directly towards the sun and is not exerting any torques on this planet. So the planet's angular momentum is actually constant as it orbits around, in this case, the sun. So just like the figure skater, bringing his or her arms in closer and then spinning faster, this conservation of angular momentum means that when the Earth is closer to the sun, it's actually traveling at a faster velocity than when it's far away from the sun. Now, Kepler's second law actually was a more precise statement than, it's not just the orbits don't have to be constant velocity. It's actually that if you imagine, let's say, a line drawn from the Earth to the Sun, and as the Earth moves in a certain amount of time, so as the Earth goes from, say, this point to this point in the orbit, this line, this imaginary line, will kind of sweep out a certain area in this not quite triangular shape, right? Kepler's law says that if you look at equal times, this line sweeps out equal areas. Okay, so if the time that it takes for the Earth to go from here to here is the same as the time it takes the Earth to go from here to here, then this green area will be the same as this green area. Will be the same, if this is how far along the orbit the Earth moves in the same amount of time it took the Earth to go from here to here, this area is the same too, A3. So Kepler's second law actually says a line from a focus of the orbit of the orbit to the planet will sweep out equal areas in equal times. All right, and finally, Kepler's third law of planetary motion is a generalization, again, of what we said at the end of 5.2.1 about what is the orbital period as a function of the distance between an orbiting object and the thing it's orbiting around, right? So remember here, we said that the square of the angular speed is related to 1 over the cube of the distance between the objects. Kepler's third law says that the square of the orbital period okay, so not what the angular velocity is, but how long it takes to go all the way around one complete orbit. The square of the orbital period is proportional to the cube of the distance, the cube of the average distance. From one focus, average distance from the planet to a focus. Okay, and so what does this mean? Like along this trajectory, as the Earth moves around the Sun, the Earth is at different distances from the Sun. Okay, so over here it's pretty close. Over here it's a little bit farther away. I've kind of exaggerated how stretched out this ellipse is, but it makes it easier to draw. So at different times of the year, the Earth is different distances away from the Sun, and if we take the average of all of those distances, Kepler's third law says the amount of time it takes the Earth to orbit around the Sun, say, the square of that time is proportional to the cube of that average distance. Okay, and compare this to our kind of uniform circular motion due to gravity result, which said that the square of the angular speed is inversely proportional to the cube, right? This was actually g times the mass of the Earth divided by r cubed. Well, the length of time it takes to go around a circle is inversely proportional to how much of the circle an object goes through per unit time. So you can actually see that this is like a generalization. Kepler's third law is like a generalization of what we knew about uniform circular motion. Okay. Now, the important thing, though, is that I've presented all of this stuff kind of in backwards chronological order. Kepler observed the data from this other astronomer and formulated these three laws without knowing, forces being related to accelerations, without knowing all of this stuff about conservations of momentum, so on and so forth. One of the triumphs of Newton's laws of motion was actually that starting with Newton's laws of motion and applying them to not just straight trajectories but circular motions, combining the laws of motion with this universal law of gravitation, you can actually understand where Kepler's laws come from. See, Kepler didn't have a theoretical basis for his laws. He just said, these laws describe the data we have. Newton was able to say, here's a set of principles that I can derive Kepler's laws from. And that was like a crowning achievement of 16th century and 17th century, well, 17th century and 18th century science.